I'm Johnny, and this is a SciTunes video explaining one of the deepest and most far-reaching ideas in science: energy. I'll be explaining what it is and all the different ways it can be stored or moved around. And of course, there'll be some songs too.
Can't be made or destroyed. There's many ways it is stored. Change means it's shifted to new stores. And the energy after is the same as before.
Have a look at this. When the purple ball hits the orange ball, it slows down and the orange ball speeds up a bit. It's like it passed on some of its movement. But how can I pass more movement onto the orange ball? Perhaps I can make the purple ball go faster. Yep, that worked. But what if I drop it from higher up? Yep, that worked too. But what if we use a heavier ball? As you might expect, faster, higher and heavier things pass on more movement. And that ability for something to pass on movement is what we call energy. In 1740, a scientist called Emily du Châtelet showed that energy is conserved, which means there's always the same amount before a collision as after. I'll show you what I mean. When I lift the ball, I push it upwards, and the higher I lift it, the more I push it. When we push or pull things to give them movement, scientists call that mechanical work. So higher, heavier things store more energy, but only because there's gravity. So we say they've stored the energy gravitationally. But when I drop the ball, it speeds up because the Earth's gravity has pulled it towards it, doing mechanical work on it. It's now stored in its movement, or we could say stored kinetically. And Emily du Châtelet showed that you can calculate the same number for the kinetic energy when it's at its fastest, the gravitational energy when it's at its highest, and the same number for the work I did in lifting the ball.
If you're an engineer designing cars or planes, how do you know that when they're used they're gonna be safe?
You can make a prediction that's so precise it's insane, with equations, calculations, and imagination.
What will you need to know?
Speed, distance, mass, and time.
What are they?
Scalar quantities that only have size, but some quantities are vectors with direction besides. That's how velocity, acceleration, and force are defined.
But what's a force?
Push or pull,
Like magnetism and weight.
they are the ones that can still pull when the objects separate. But compression and tension and air resistance relate. Their contact forces,
Like a normal force and friction.
add them together to treat them like there's one. I use resultant forces to predict the outcome.
Push it.
Change your shape, your speed, or your direction.
Pull it.
When forces balance, you won't change momentum.
Push it.
Force is mass times acceleration.
I will pull or push you back in every situation. Tell me what you know about gravity.
Bigger, closer things pull more attractively. To find the weight, multiply the mass by G. The field strength on Earth is roughly 10 newtons per kilo.
And if I'm stretching a spring,
It's smart to see that the tension and extension go proportionally.
then what's a moment?
Turning force like spanners need. Force times distance from the pivot perpendicularly.
Okay, but how do forces link with something's energy?
Force times the distance moved is work that's done mechanically. It's the energy shifted between stars. An example could be shifting by lifting to be stored in things gravitationally.
So what's momentum?
Mass times velocity. And if it's slow, then something's motion changes easily with
Push it.
change your shape, your speed, or your direction.
Pull it.
Force is balance, you won't change momentum.
Push it.
Force is mass times acceleration.
I will pull or push you back in every situation.
If energy is conserved, it can't be made or destroyed. It just gets moved around from store to store. So when I drop it, it should swing over there and come back with just the same energy and, well, it would hit me in the face. Phew. The ball didn't hit me in the face because when it was flying through the air, it had to push the air out of the way and transferred some energy to it. And it's actually really hard to keep energy in one place. It just kind of dissipates into the surroundings. Then it becomes useless. But you know what? There are useful ways to send energy from one place to another. Or put another way, how do I move something over there from over here? Up first is projectiles. We can pass movement from over here to over there by throwing something, like an angry bird. When I pull the catapult back, I store energy in the catapult. Oh, that's another store of energy, elastic stores. And when I let go, fire! See, we made the piggy move. Now up next is flowing. Rivers and wind have been used for centuries to capture useful energy. I can get the wheel to turn from over here by allowing the rope to flow around it. Flows are great because you can continuously capture energy as long as you don't run out of something to flow. You can also send energy from one place to another through a substance using a wave. With a wave, they go through a wobbly substance where the particles might be able to move up and down, or sometimes side to side. If I move this part of the substance up and down, it'll move the next bit of it up and down, which will move the next bit of it up and down, which will move the next part of the substance up and down, which you get the idea. When I make a sound, I make the air wobble. That wobble is passed as a sound wave through the air, it hits your ear, it wobbles a bit in your ear, and sends a message to your brain!
Move up, move down, then pass the movement around. Move side to side, then spread the movement out wide. Move up, move down, then pass the movement around. Move side to side, then spread the movement out wide.
Up and down, or side to side. Waves of how vibrations spread with a seismic sound alike. Up and down, or to and fro, transferring energy and information as they go. If you wanna send energy without matter being sent to, get a substance vibrating and watch the ripple spread through. Seismic waves go through the earth, the sound can ripple through air. Light don't need no medium, and that's why it's everywhere.
Up, down, pass the movement around. Move side to side, spread the movement out wide.
Vibrations in the transverse wave are perpendicular to the direction that the wave will go. Peaks and drops occur. Seismic S waves, water waves, and light are examples. But seismic P and sound waves are longitudinal. They have vibrations parallel to the direction they go. Compressions, rarefactions, form as the shaking to and fro. Up and down, or side to side. Waves are how vibrations spread with a seismic sound alike. Up and down, or to and fro, transferring energy and information as they go.
Move up, move down, spread the movement around.
Ooh, periods of time for one vibration to complete, and the number of waves that pass the point each second's frequency. The amplitude is the middle to the vibration's maximum, and the wavelength is the distance moved when the period is done. Wavelength times by frequency will give a ripple speed, and if you are describing waves, they're all the words you need. Up and down, or side to side. Waves are how vibrations spread with a seismic sound alike. Up and down, or to and fro, transferring energy and information as they go.
Get down.
Rub your hands together. You're doing mechanical work because you're pushing against friction. What do you notice? Because my hands are getting warm. In the 1840s, James Joule did an experiment where he stirred water and he showed that the temperature raised. Might take me a while to make my tea like this though. But he'd shown that mechanical work and heating were actually the same thing, bringing together two areas of physics, the study of forces and the study of temperature. And that's why the unit of energy, the joule, is named after him. But hang on a minute, my hands are warmer. But are they moving faster? James Joule had a very clever answer for this. He got us to imagine that substances are made of tiny particles. So maybe my hands aren't moving faster, but what if they're made of tiny little things that are jiggling on the spot faster? Now, not only did this explain where the energy went, it also explained a lot more too. Let me show you. Now we know that James Joule was correct. Everything is made up of tiny, weeny, teeny little particles called atoms, ions, or molecules, and they stick to each other a little bit like these Velcro balls. Because they're stuck together, even if I do a little bit of work and give them a little shake, they just jiggle, they keep their shape, a bit like solid, like ice. But if I shake them a bit harder and do a little bit more work, they lose their shape, but they're still a bit stuck together, like liquid water. How can I turn them into a gas? Well, I do more work. Steamy. The more a substance's particles move apart and jiggle around, the more thermal energy they're storing. And if we make them move around more, we call that way of transferring energy heating.
Why is lead so dense and why does ice melt when it's warm? Why do liquids flow and take on their containers' form? The reason substances behave in the way they do, they're made from particles that bond and move. Atoms, ions, molecules make up our substances, and heat in them makes these particles break bonds or move at greater speeds. The way they bond and move gives substances their properties. Solid, liquid, gas, that's the particle theory. Solids are as close as they can be. That's why compressing them cannot be done so easily. It's also why they tend to have the greatest density, more kilograms of mass per meter cubed. Stuck together tightly, their particles vibrate. Those bonds are why a solid keeps its shape. When you're heating up a substance, you raise its temperature by doing work on particles to make them vibrate more. They push themselves apart a little further than before, but the bonds can hold the particles in place. Strong bonds make it harder to vibrate them rapidly, so a substance with strong bonds has higher heat capacity. Atoms, ions, molecules make up all substances, and heat in them makes these particles break bonds or move at greater speeds. The way they bond or move gives substances their properties. Solid, liquid, gas, that's the particle theory. Eventually the temperature will no longer increase. Particles won't vibrate any faster till some bonds release. The energy that breaks the bonds is known as latent heat. Then the solid can begin to melt. Particles and liquids stay close, but bonds can split. So a liquid flows but might only compress a tiny bit. Atoms, ions, molecules make up all substances, and heat in them makes these particles break bonds or move at greater speeds. The way they bond or move give substances their properties. Solid, liquid, gas, that's the particle theory. Energy and all the bonds will break. Boiling liquids bubble as their particles separate. Gas whizzing around and round and speeds around in ways. Hotter gases particles have higher average rates, spreading out as much as possible to fill up inner space. Colliding with the sides of vessels, they accommodate more collisions every second. The pressure escalates, rises with the temperature as the particles accelerate. Atoms, ions, molecules make up all substances, and heat in them makes these particles break bonds and move at greater speeds. The way they bond or move gives substances their properties. Solid, liquid, gas, that's the particle theory. Make up all substances, break bonds and move at greater speeds.
So I've put some alcohol in this bottle. Watch this. Whew, that chemical reaction really warmed things up. And when energy is released through a chemical reaction, we say it was stored chemically. Fuels like that alcohol are great chemical stores of energy. They store loads of it. And to understand why, we're going to have to look inside the molecules themselves. Chemical reactions happen when molecules bump into each other. If they bump into each other with enough energy, they fall apart. If they stick to different atoms when they recombine, that they're more attracted to, they come together moving faster, and the molecules at the end are jiggling more. They're hotter! All this talk of atoms and molecules sticking together, but why does it happen? It's a bit like the reason this balloon sticks to me. Magic! No, only joking, it's electrostatic charge. See, atoms are made from even smaller things, electrons that spin around a nucleus. And the reason that electrons are attracted to the nucleus is, well, we say the electrons have something called negative charge and the protons have positive charge. Opposite charges attract, and things that have the same charge repel. Now, if we can make stuff move with electric charge, it must be storing energy, so we say it's stored electrostatically. In here is a battery. Batteries have different charges at their ends, so they're like an electrostatic store. And if we connect their ends in a circuit, we can make electrons flow through the circuit. We call that transfer of energy electricity.
Let's talk electricity. It makes the lights shine. It gets you online, powers kettles for your tea. And when you talk about the charge in a circuit, you mean electrons that are free. My brothers, sisters, and me. Physicists will agree that a Coulomb will be about 6 billion of us. That's a big family. We are electrons getting pushed around in a wire. If we get faster, there's more of us. Our current is higher. Potential difference is the reason that we are flowing, but we get stuck. We stop flowing if that circuit is broken. Current's the rate that we flow, the number of us that go. Charge over time, 1 Coulomb per second is 1 amp, you know. And the reason that we move is we're getting pushed to do this by negative charge and pulled to positive charges. But you knew this. We're always working as a team to transfer energy. The joules transferred per Coulomb is the potential difference, PD. Yo, it is measured in volts, so the work done is Q times V. If volts go higher, then our current increases. We are electrons getting pushed around in a wire. If we get faster, there's more of us. Our current is higher. Potential difference is the reason that we are flowing, but we get stuck. We stop flowing if that circuit is broken. We get obstructed though, yeah, we collide as we go with the ions in the wire, which heats up, that's why a bulb glows. So we make a ratio between PD and current flow. V equals I times R, which is resistance measured in ohms. The rate that we transfer the energy, E over T is power P, it also equals IV. And what about safety? When I get too lively, earth me, insulate my wires, use a fuse to stop me. We are electrons getting pushed around in a wire. If we get faster, there's more of us. Our current is higher. Potential difference is the reason that we are flowing, but we get stuck. We stop flowing if that circuit is broken. We are electrons getting pushed around in a wire. If we get faster, there's more of us. Our current is higher. Potential difference is the reason that we are flowing, but we get stuck. We stop flowing if that circuit is broken.
When electrons move through a wire, like in an electric circuit, they create a magnetic field around them. So, if you've got a wire with a current going through it near a magnet, you might get some movement. If there's movement, then magnets must also be a way of storing energy. Magnetic stores. Now, you might be thinking, how do these charged particles give each other a push from a distance? Well, the answer is, the energy is transferred through a wave, a very special type of wave, called an electromagnetic wave. And light is an example of one of these. This laser is a very intense and powerful beam of light, and it can do a lot more than just move electrons. Look what it does to this light mill. It can even pop balloons. Lighting was our last way of transferring energy, and there's many more types of light waves that we can't see. Here's a little chorus to remind you of all the different waves on the electromagnetic spectrum.
Radio waves, their frequency's low. Microwaves from a mobile phone. Infrared feels like heat to me. Visible light, that's what I see. Ultraviolet tans my skin. X-rays show me my bones within. Gamma rays may make me scared. Electromagnetic waves are everywhere.
Now, gamma rays were first explained by Marie Curie. She explained that inside the nucleus of an atom there are protons and neutrons that stick together. But of course protons are positively charged, so if an atom gets too big, there's so many protons all repelling each other that little chunks fall off. These are called alpha particles. Subatomic nuclei have too many neutrons to be stable, and they spit out high-energy electrons called beta particles. These nuclear reactions also cause gamma rays to be emitted. So much radiation! That's why we say substances with unstable nuclei are radioactive, and they are stores of nuclear energy. A lump of uranium this size stores enough energy to power your entire life.
Radioactive, 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 radioactive.
In the middle of every atom you'll find a nucleus which will be made of protons and neutrons that strongly bind, and most nuclei never will change. But large nuclei that are bigger than lead can't hold all their protons in place, and some rare isotopes have too many neutrons, are not enough for them to be stable. They may decay and radiate particles or high energy EM waves. As their nucleus changes, they change their name. As their atomic number does not stay the same. Unstable nuclei randomly decay, spit out an alpha or a beta, then emit a gamma ray. They may be dangerous, watch out, but we use them every day, yeah.
Radioactive, radioactive.
Ooh, becquerels are decays every second. Their activity, it decreases with time as fewer unstable nuclei are left to decay randomly. And ooh, half-life is the time for it to go down by half naturally. For some isotopes this will be seconds or millions of years if they have more stability. Unstable nuclei randomly decay, spit out an alpha or a beta, then emit a gamma ray. They may be dangerous, watch out, but we use them every day, yeah.
Radioactive, radioactive.
Our last energy store is linked to perhaps the most famous equation of all time, E equals mc squared, and it tells us that you can calculate energy by timesing the mass of something by the speed of light squared. It was discovered by Einstein when he was thinking about how light travels. The speed of light squared is a redonkulously large number, which means that mass stores a redonkulous amount of energy. The mass of this egg is enough to power your lifetime 400 times over. We started out by thinking about energy being the ability to make something move. But if mass is stored energy, then the answer to what energy is way more exciting. Everything is energy!
Energy, what is it?
If something's gonna cause an object to move, whether tiny as a photon or as big as the moon, we can calculate how much movement there could be, and that number is the thing that we call energy.
And it's measured in joules. I don't mean like precious jewels, I mean like James Joule.
It could be stored in stretch elastic or the movement of a ball, the repulsion of two magnets or the bonds and chemicals between an apple and the earth. If an apple wants to fall, the nuclei of atoms mass of anything at all. But whenever there's a change, we shifted energy by pushing, heating, lighting or electricity. It will go to a new store, that's what we observe, 'cause there's a fundamental law